So what we want to do over here is you have a buffer which has got 10 elements, and we classified them to be sort of low, medium, and high occupancy. And what I want to do is to use this as a running example is to talk about this. Okay. So an outcome is essentially some unknown event. Okay, something has happened. We don't know that it's always going to be that way. It's going to be there's some probability associated with it. Okay, so for example, classic example, you take a die and you roll it. You have one of 6 possible faces that shows up. So the outcome is one of these 6 things. Okay. In the case of this buffer, what you're saying is that we don't know what the occupancy is at any point in time. Okay, or we actually, in the example, it's carefully set up. We know in the past what happened. We have a trace, so we know the time history of the past, and what we want to do, though it's not actually stated that way, is we want to use the past to predict the future. So we want to say that the distribution or the probability with which certain buffer occupancy has been achieved in the past is predictive of the future. So in some sense we are assuming that the future is like the past. But at any rate, we want to know what are the possible outcomes. Okay, see, outcomes over here are going to be what are the values of the buffer. So the buffer is either going to have 0 elements, 1 element, all the way up to 10 elements. So the set of outcomes, okay, is going to be basically 0, 1, 2, all the way up to 10. We can't have more than 10. We can't have fewer than 0. So that set of distinct and mutually exclusive outcomes is called the sample space. Okay, so these are the outcomes. Outcomes belong to this, and this is the sample space. Okay, and we typically denote this as S. Okay, so any questions on this? Yes.
In the question you had mentioned the entry in the log trace as,
I'm sorry, say it again.
the entry in the log trace
Yeah.
has a time and the buffer occupancy as the tuple.
Right.
So I guess like the space, what is it? The sample space.
Yeah.
Is infinite.
Yeah. Well, okay. So if you're taking the timestamp into account, you mean? Yeah.
That constitutes the entry.
Right. So when you talk about logs, you know, we have to think what's the purpose of this log. The purpose of this log is not to have an infinite sample space. The purpose of the log is to say this is the buffer has certain values in time, right? You're taking a mathematical interpretation. I'm taking engineering interpretation, right? If you were to say I have an infinite time dimension sample space, yeah, sure, you can have an infinite sample space. But here, we are looking at a sample space of just the outcomes of buffer occupancies. Right. Yes. Greg, yeah.
You said that the outcomes actually logged as the level, so low, medium, and high.
No, I did not. I said that the logs, change in occupancy is timestamp and new buffer occupancy. So the buffer occupancy is a value, right?
But you never said the buffer occupancy was at the level, so medium or high.
Oh, I see. I said the buffer occupancy will be classified as low, medium, and high. Maybe it wasn't clear. The idea was that the buffer occupancy, which is one of these outcomes, is classified as low or medium or high, right? So the buffer occupancy is to be low. That is what we're not defining the buffer occupancy, we're defining the occupancy to be low as having that value. Okay, so the outcomes are over here. Okay. Any other questions? So generalizing from this, what we're trying to say is that if you have any event where we can have distinct, mutually exclusive, so those are the 2 characteristics, they have to be distinct so we know the difference between one and the other, and if one happens, the other does not. So these are called mutually exclusive. In this case, the set of these distinct and mutually exclusive outcomes is called the sample space, and it can be finite as we have over here, or if you take a dartboard, you take a unit circle, you just pick points at random, well, we have an infinite number of points inside the unit circle, so that's going to be infinite. So you can have sample or infinite, finite or infinite sample spaces. Now, one thing we do is we can take groups of these and make them into events. So an event is a subset of the sample space. So if we were to rewrite this, just to make it clear, it has 0, I'm going to write the whole thing, 2, 3, 4, 5, 6, 7. So that's my sample space. What I can do is, and what I'm going to do for the example is that I've said if the occupancy is less than or equal to 2, then it's called low. So this subset is what we will call to be low. Everything above 8, include 8 to 10, is called high. And everything in between is called medium, so that's going to be this is medium. So notice that we've gone from outcome to subsets of the sample space, and these are the events. So this is how you define the events. So the event low corresponds to 0 or 1 or 2. The event medium corresponds to 3, 4, 5, 6, 7. Event high corresponds to 8, 9, 10. Okay, that's the definition of event. And so you want to see that the event is different from an outcome. Okay, so any questions about that? Okay. And then we talk about this notion of conjunction of events. So we can say, what about the event? The event can be low or we define or like that as low or medium. And that low or medium is going to be nothing more than 0, 1, 2, all the way up to 7. So those are the outcomes are going to be low or medium. That would be the set outcomes. So it's a very clear understanding of what that is. And we can think of the other event, which is low and medium. And this is going to be, of course, the event is going to be null because obviously these are non-intersecting. But you can think of events that actually do intersect. We could think of an event called low dash medium, which is maybe this one is called low to medium. Okay. We could define that event low dash medium, and then we could say, okay, then that is going to be an event which is overlapping with this, and so or the and of low and low medium is going to be the value 2, for example. The outcome 2 is going to be both. Okay. So we don't need events need not necessarily be mutually exclusive. So that's conjunction and disjunction. Okay. So yeah. What is conjunction?
Yeah, it's like combining two events.
And yeah, so this event E, let's say E is defined to be the conjunction. E is said to occur only if both have occurred. Okay, this has to occur and the other thing has to occur. Whereas this event E occurs if either one occurs. So if any of these outcome happens, then we'll say that the event E, which is the OR, has occurred. So definition of the event. Okay, so I mean, we can say that the event is have some event, and I'll say if event E1 happens or event E2 happens, either way I'll say event E happens. Okay, that one is called the conjunction. Okay, and the disjunction or the and means that they both have to happen, otherwise I'll say the event did not happen. Okay, that's the definition of the disjunction happening. Oh, sorry, I'm confusing this. Okay, oops, this is the okay, never this. I say or is disjunction. Oops, and sorry, and is the conjunction. I prefer to use or and, but this is and, this is or, rather than disjunction, conjunction, which are left over from the 19th century. So nobody uses it. We all say in computer science, we just say and or, we know what it means. And means they both A and B happen, and or means either A or B happened. Okay, so. And conjunction and disjunction we put in textbooks to confuse people. Yes? You have a question? No, okay. All right. There are some axioms of probability which I'm going to skip. I want to actually focus just a little bit of time on subjective versus objective probability, and I'm going to leave this one here and talk about that, and then we'll take a break. So there's been a long fight going on between the two schools of thought on probability, between subjective and objective probability, where in objective probability, there's this feeling that probability arises and can be measured objectively. Okay, and the two ways of doing it, one is using a combinatorial approach. You're going to say these are all possible ways something will happen. I'll enumerate them using some combinatorial algorithm, and then I'll tell you, well, what happens. because they're all equally probable or something like that. So if I take a die and I roll it, it doesn't matter what I think. Okay, the probability of any phase for a fair die is going to be 1 over 6. That's objective. Okay, this doesn't matter who is measuring it, it's always going to be 1 over 6. That's objective. The other way it could be objective would be if you're going to take this buffer measurement example, I'm just going to measure it, and I take longer and longer measurements, and if the buffer happens to be what's called stationary, which means that it is, it's not changing its underlying behavior in some dramatic way, then as the number of samples goes to infinity, we're going to get some frequency of each buffer value, and we'll call that the probability of the buffer value. So let's say we take 100 million samples, and the buffer value 2 shows up 1 million times. You're going to say, okay, it's 1 million over 100 million, so with probability 0.01, that is the probability of at any random time you look at the buffer, it's going to have one packet in it, probability 0.01. Again, no person is involved. It's just a measurement. You could presumably have a computer go through the whole thing and say, okay, it happens this out of that. Okay, that's what's called frequentist approach. But if somebody were to come and ask you, what is the probability of rain tomorrow? Okay, and you say it's 40% chance of rain. Where is the underlying sample space? What is the frequency that's being measured? One could say, well, if all possible days that look like today and all possible weather systems that look like the weather system right now, etc., going off into the infinite past of the universe, some number of times you had rain, some other number of times you didn't have rain. Okay, so that's what it is. So, okay, you can kind of get away with that. But what if you go to a horse race and somebody says, what's the probability this particular horse is going to win, right? And you say, I think it's a 20% chance of winning, but you haven't run that race yet. It's not like you had an infinite number of races to choose from, so you can't have a frequentist approach. Similarly, when we study game theory and we have certain probabilistic moves, we don't know what the probability means, yet we have an intuitive feeling of this. And the best way to model this is in terms of a bet. Okay, and the subjective probability, as it's called, because it depends on the subject. A person is to say, okay, I'm going to ask you to place a bet, and if that comes up, you get some money. If it doesn't come up, you lose money. And tell me how much money you're willing to bet. Okay, I mean, so what is the ratio of odds for this? And so you can take any event, and you can, with that event, you can associate a subjective probability by asking somebody to bet on it, on the theory that nobody wants to lose money. Okay, so you'll always choose intrinsically what it is. So let us say that you have a horse race, and you have a person who's an expert bettor who understands how horses run, etc., and has taken all the variables into account, and you say, okay, what is the probability of this horse winning? They say 20%. They say, okay, with 20%, here's what I'm going to do. If the horse wins, I'll give you $5, and the horse loses, you give me $1. Okay, so you can change these amounts so that the person says, it's not worth it. I'm going to lose money on average. Okay, so if it's 20% chance of winning, and then a $5 to $1 is going to be even exactly. They're neither going to lose nor they're going to win. On the other hand, if you say, okay, if the horse wins, I'll give you $5 and a penny, and if it loses, you owe me a $1, then they'll actually take the bet. Okay, so you can say, okay, that's the point at which they say, fine, it's actually worth it. I'm going to make 1 penny on average, actually 1/5 of 1 penny on average, which as a rational bettor, they're going to actually prefer. Okay, that 1/5 of a cent is worth something to them. So this is subjective probability, and when we get into more complicated systems, it's very hard to tell is this objective or subjective or a combination of the two, and there's been a lot of debate about this. For everything to do with information theory, we'll be using only objective probability. We're not going to do subjective at all, whereas everything to do with game theory actually pretty much uses subjective probability. So yeah.
Can we standardize the subjective probability?
No, it depends on who it is, right? It's what it's worth to you. Since game theory deals with people, it's always using subjective probability, and information theory is using is models of physical systems. It uses objective probability, and computer networking by and large we do for subjective probability. Okay, let's take a break, and then I'm going to go a little bit into conditional probability and then into random variables, which are the two things I wanted to cover here. We looked at outcomes and events and so on. I want to spend a little bit of time talking about, maybe I should mention, okay, processes. I want to joint processes. And then conditional. Okay. So a process is an intuitive idea, and it's not something that I'm going to explain, but a process can be you can think of it as something that creates outcomes. Okay, so if I roll a die, rolling the die is a process and it has an outcome. So we have some kind of process P, and arising from it is some outcome. And as we know, the outcome is some part of some sample space. And let's call that S. Okay? So the process is some undefined thing, but we know that it results in outcomes. Okay? So the process of packet arrivals to the buffer is the process. The buffer occupancy, the number of packets in the buffer is the outcome. And that outcome, as we see, comes from some sample space. Okay? So now, that's the process. But what about a joint process? A joint process basically means that we have one process followed by another process. Okay? We have one process followed by another process. And so we can call this process P1, resulting in sample space S1, and then followed by some other process P2, which results in some outcomes, and that is we call sample space S2. Okay? And now we want to talk about these two outcomes at the same time. Okay? And this together we will call a joint process. And they could be simultaneous or subsequent. Okay? For the moment, we haven't really specified any time ordering on the processes. So for example, we have these two buffers. So the first buffer has got some occupancy. So that's called that buffer 1. And then we have another buffer which has some other occupancy. We call that buffer 2. And so we can talk about the event, which is, let's say there's 2 packets here and 3 packets here. So we'll call that as 2, 3 in some tuple, and we'll call that the joint outcome. Okay, so the two processes are doing the thing, and at some point they result in some outcome, and I can talk about joint outcomes. And obviously this generalizes to any number of outcomes. You can have finite or even infinite number of simultaneous outcomes. Okay, so obviously we're kind of interested in things like what is the probability of this particular joint outcome, 2, 3. Okay, what is the probability of this joint outcome? We call that the joint probability, and I'll discuss that further on Friday. Okay, but now we're going to talk about a slightly different thing that has to do with joint processes, which is that we've seen some outcome from the first process, and we want to know whether that tells us anything about the other process. Okay, so if you have these two buffers like this, I haven't said anything to you about the underlying system, so we actually have no clue. Maybe they are related, maybe not related. Maybe if I have buffer occupancy high over here, this would be also high or low or medium or whatever. We don't know, right? But let's take a concrete example. Let's say when it's cloudy, there's a 30% chance of rain. So I have actually got two outcomes. One is the whether it's cloudy or not, and the second one is rain or not. I have two outcomes, right? So we can view the first process as being the cloud process, and then second one being the rain process. And then the outcomes over here in the sample space is trivial, either cloudy or not cloudy. Okay, we're not going to go into intermediate cloudiness, it's cloudy or not, and it's going to rain or not. Okay, so one could state a rule of the thing that if it's cloudy, there's a 30% chance of rain. Okay, but if it's not cloudy, there's 0% chance of rain. So we now have a kind of a relationship between the two, which says that the outcome of the first process has an influence on the outcome of the second process. Okay, and so one can think of the following situation. Somebody asks you, what's the probability of rain? You say, I don't know, it's something, there's 20% chance of rain. And then somebody else comes and says, look, I'm telling you it's cloudy. Now tell me what's the probability of rain. So at this point you're saying, oh, I'm going to revise my estimate upwards because I know when it's cloudy, there's more likely chance of rain. Okay? So you can see that there is this notion of independence and dependence of events, or outcomes of events. So independence and dependence of processes. When two processes are independent, if you have some set of outcomes from some sample space with some probabilities associated with them, knowing this additional information about this outcome gives you no additional information. You don't change your mind. You don't say anything. Nothing has changed. It's just the way as it was. In this case, we'll say that these two processes are independent. On the other hand, if knowing the outcome of some other process allows you to revise your expectation or allows you to revise your prediction of the outcome of this process, then we'll say they're dependent. Okay? So there are these essentially these issues. So we have notion of conditional probability, and they're all related. Conditional probability, independence, and dependence. And it's important to realize that these concepts arise only when we have joint processes. Okay, we don't really have any notion of independence and conditional probability, etc., unless we have joint processes. Okay, so this is very important to realize that. So when we talk about joint processes, one of the most common mistakes is to not keep track of the underlying sample spaces, because they could be completely different. You could have S1 and S2, and they could be totally different. For example, in this case, for rain and cloud, this sample space was cloud, this sample space was rain. Okay, and so we have outcomes cloud and rain, cloud, no rain, no cloud, rain, no cloud, no rain. Right? We have actually these four possible tuples. Okay. All right. So, any questions about this over here? So, yeah.
Four possibilities, but when it's conditional, how come we have the rain when we don't have cloud?
The probability is 0. Yeah. We can have 0 probability outcomes. Right? So probability is 0. Okay. So, what we're going to do over here is, it turns out that there is a definition of conditional probability. Okay. And you can argue it's a good definition or bad definition or something like that, but there's axiomatic theory of probability, and the axiomatic theory which I've sketched over here, we are going to be able to derive exactly what we mean by a conditional probability, or define what it means, which is consistent with the axioms. Okay, and this allows us to go forward and do a lot of other things. So I'm going to just write down the definition. So this definition of conditional probability is not, it's not something that you have that you have any choice with, but we define, first of all we say the probability of f, some event f given some event e, okay, is on this joint space S cross S, so we denoted this is given by f and E and f over S E. Okay, so this is the definition. So we're saying, so we read this as probability of f given E. So probability, for example, of rain given cloud is going to be defined as the probability of the joint event f and E. Okay, so this f and E is a tuple, like this 2, 3 tuple. Okay, it's not an individual number, it's a tuple, f and d, because it's on the samples, on the product of the sample spaces, and over the probability of, divided with probability of E. And if these sample spaces are different, then we just annotate it like this: S1, S2, f given E is over S1, E. So we can, of course, have different sample spaces as well, as I've shown over here. So remember that the f and E is on a product sample space. Okay, and it corresponds to joint events on these two different processes. They're not, okay, and that's where typically people make mistakes. They don't understand that over here. Okay, and in the text I've given some examples of this, which I assume you've read, so I'm not going to go over there, and there is this famous sort of Monty Hall problem, which is somewhat confusing, but hopefully I've explained it here in a way that makes sense. And the whole issue here is that the sample space changes once you have more information. When you have more information, the sample space actually reduces because these are zero probability events. As Navid was saying, probability of no cloud and rain is 0, so we can eliminate that from the sample space, which is what's going on in the Monty Hall. Okay, so any questions about this? This is just a definition, and again, you've probably all seen this before many times, so that's why I'm kind of going through it pretty fast. Any questions about? But I guess the point I want to make here is that first, there are 2 probability spaces, and second, this is a definition. This is not like, oh, I'm deriving it from something. No, this is by definition, this is what it is. Okay, given this definition, very simple substitution allows us to come up with something somewhat surprising, and that's called it's called Bayes' rule or Bayes' theorem. So I'm just going to write down Bayes' theorem. And Bayes' theorem is basically going the other direction. So this is F given E. So E is sort of what so we know that E happened, okay? And so with the direction causality is E happened, and then we know something about F. So we have a joint process and E happened, and then we know we're going to kind of make a statement about what is the probability of F happening. In the Bayes' theorem, we go in the other direction. So we're given F, and sort of this implies some E, E1, E2, whatever the probability events. So you want to say F happened. We know it happened, okay? And we want to know which of these E1, E2 priors happened. So we're kind of working backwards, okay? So typical example is this. You go to the doctor, you get a medical test, they do a blood test on you, and they say your cholesterol level is high, okay? So now that's F. We know it's happened, okay? Why is your cholesterol level high? There could be 10 different reasons. It could be genetic, maybe you had a heavy breakfast, whatever it is. There could be many different causes. So we want to say, given that this outcome happened in the joint process, what are the possibilities of the other, of the priors, as they're called, okay? So here you're given E, I'll circle it. You want to know what F is. Here you're given F, and you want to know what are the probabilities of the various E's. And what Bayes' theorem allows us to do is to write this down like this. So the probability of the ith event E sub I given the outcome F. So remember, E given F, not F given E, is given by this one. So P F given E, P E I over sigma I equals, this is for when we have n possible outcomes. This is for finite spaces. Okay, so derivation of this rule is in the text, and it's pretty straightforward, but let me explain to you what it is. This over here on the numerator is basically the F given EI is basically one chunk, and there are n of these things in the denominator. Okay, it's really one of these n things has been taken. So you can think of it as a weighted average. Okay, where there are n elements in the denominator, one of the numerator. So this is similar to basically Wi over sigma Wi. Okay, just think of it as that. Okay, and this term PFQ and EI is basically the amount of probability we can ascribe to the prior EI. Okay, so you have F, some F has happened, and we had, let's say, 10 different possible priors. So you have a high cholesterol result, you have 10 different causes, and this rule, Bayes' theorem or Bayes' rule, tells us how we can work backwards to derive what prior event could have happened, what prior event could have caused this because of this. Okay. So I'm going to just state this rule here because I wanted to put it up next to conditional probability, On Friday, we'll talk about Bayesian networks, and then there we'll use this rule and do an example in some more detail, and it'll become much more clear what's going on. But for those of you who've seen Bayes' theorem, the main, you've seen this already. For the rest of you, the main important thing here is that conditional probability is F given E, and Bayes' theorem is E given F. Okay, so it's the other direction. That's what we have. And this is very, very important for many things having to do with AI and so on and so forth, where we see something and we work backwards and say, oh, it must have been that in the past this happened. Okay, so you can update our understanding of the state of the world based on our actual observations. Okay. Any questions about this over here? Okay, so I know that I'm going somewhat fast over here, but the reason is because I want to get into random variables, and then we'll spend some bit more time over there. And I'm going to again, I'll come back to this anyway later on. So let me jump straight to random variables and look at the homework question again. So we've talked about outcomes. We talked about events. So outcomes are a process happens, and at the out of the process we get some outcomes, and outcomes are distinct and mutually exclusive, and we club them into events. And we can talk about probability of events, but we don't have any way right now of talking about the relative values of these events and so on. And so what we'd like to do is to have this notion of a variable. Okay, this variable says x, and we want this variable to take on certain values in some domain. Okay, so the value is x1, let's say x2, x3, and these values are chosen from some domain, and in almost all cases our domain is going to be the real numbers. So these are three different real numbers. So we're going to say the variable x assumes the value x1, x2, x3, but it assumes these values with some probabilities. Okay, and so we have some probability. We use small p for this. So you're going to have probability small p x equals x1. We have some probability x equals x2, and there's some probability x equals x3. Okay, so the way we model it is by saying that these x1, x2, x3 are probabilities that arise due to some underlying sample space and some underlying outcomes and some underlying events. So we have some sample space S over here, and I'm going to draw it vertically just to keep it consistent. And so we have some outcomes, O1, O2, O3, and all the way up to, let's say, ON. And I'm going to club these into some events, call this event E1. And clearly there's going to be some probability capital P of E1. And there's going to be some other set, and there's going to be capital P of E2. And there's going to be something over here, some set over here, capital P of E3. And this capital P of E3 corresponds to small p of this. Okay? And so the random variable is not an outcome. The random variable has a probability depending on an outcome, okay, on a set of outcomes. So to make this clear, let's look at the buffer occupancy. Okay, so the buffer occupancy was in the range 0 to 10, and so it is 0, 1, 2, 3, all the way. Let me just draw 8, 9, 10. Okay, and if you remember, we had these events where we called this event to be the low event, this event to be the high event, and this to be the medium event. So we can think of some random variable. Let's call the random variable O for occupancy. Okay, so O is going to be basically either have the value low, medium, or high. Okay, in this case, O is not, the domain is not reals. In this case, the domain is the three values, low, medium, and high, right? So the domain is these three things. And what is the probability that O is going to be low? So P, small p, O equals low is equal to capital P probability. Can you see this? No, you can't see this. Okay, I'm going to do it on the other side. Okay, let's do it over here. So the small p probability that O equals low is equal to the capital P probability of the event low, which is going to be capital P of either 0 or the outcome applied, because it's mutually exclusive P1 plus P2, okay? That's the probability of the random variable O being low, okay? So you can see how the random variable relates to a value in its domain, okay, which is different from the outcomes, which are 0, 1, and 2, which are part of this event over here. And because these outcomes are always mutually exclusive and distinct, we can always write these probabilities for this event. You can always take an event and break it up into its underlying outcomes like this and write it out like this. So the capital P always stands for probability for events and outcomes, and small p is the probability achieved by taken by random variables. Okay. Are there any questions about this over here? So now in this case, the question was what is the random variable? The random variable would be, let's say, O for occupancy, and its domain is low, medium, high, and it corresponds to these values over here. Now, because the random variable only takes 3 values, you can think of this as having a histogram like so, low, medium, and high, and where the probability P is on the y-axis, and then this is low, this is medium, this is high, and this we call a discrete random variable. On the other hand, we can see continuous random variables where the x-axis would be real. So the question was, is it discrete or continuous? Well, it's discrete. And then how do we compute this? Okay. So remember, the frequentist approach says that the probability is sort of the fraction of the events or outcomes which have that value. So let's take a look at the trace, and the trace is going to be looking like this. So the time, of course, is continuous, and here is the occupancy level, or the outcomes if you want. So it only maps the changes. Let's say for a long period of time it was at 1, so it's going to be very long, and at some point t1 it goes up to, let's say, 3, and then it goes to 3, stays there for some period of time, and it goes down to 1 again, and 2, etc. It can have, so generally it will have some kind of step function going up and down, where all we have are these values over here. We only have the x, they're not equally spaced, okay? So what we need to do is to, taking the frequentist approach, you need to compute the total amount of time that it has a particular value. So let's say that this value 1, well, this is the whole area over here from 0 to t1. It was 1 again from here to here. It wasn't 1 again ever again in this particular example. So if you take this value plus this value and divide it by the total time, we will ascribe that the probability of having value of the buffer having a value 1. Okay? And so what we have to do then to compute this conditional this discrete probability distribution is to figure out the all the times. Okay, so we're going to figure out all the times that the level equals 1. So the sum of all the times level equals 1 over the entire time duration t. That is going to be the probability of buffer occupancy level 1, and we're going to do this. So the probability that O is equal to low is going to be what? This we'll call as P1 equals this, and then we have similarly P0, P1, P2. We compute P0, P1, P2 in this way, and that gives you the probability that the occupancy is low, and we do the same thing for medium and same thing for high. Okay, so that should be the answer that you have. Yes. Yes. Well, so the thing is, the events are low, medium, and high, right? So the buffer occupancy, if I think I stated it quite carefully that we want the occupancy to be, so I see. So I guess the buffer occupancy is being it's ambiguous whether it's 0. Yeah, if you want to call it 0 to 11, but I wanted to say low, medium, high, but I guess my question is ambiguous over here. Okay. Right. Yeah, that's fine too. I wanted to get the idea of what its a random variable is versus what an event is, and if you understand that, it's fine.